Okay, so how do we make sense of all these chemicals? Well, of course, we've come up with the periodic table, right? So the periodic table has arranged elements in terms of how they can bond by the electrons that they have in the outer shell. So we'll get into that in a second, but you should know that, the columns, not the rows, I'm talking more about the columns here, they are arranged according to what electrons they have in their outer shell. So that's an important thing. We are going to restrict ourselves with pretty much the first three rows. Now, there are some other elements that are important to life that are further than that, like iron and a couple other things, but we're going to stick, I think, with the first three rows. So what you have here is kind of zoomed in, right? With some of these select elements on the chart, you can see that that first column, which was identical to the one back in the periodic table, right? Hydrogen, lithium, sodium. You can see hydrogen, lithium, sodium. The reason that they're in that first shell is that they have one electron in the outermost shell, right? That allows them to be pretty reactive. Basically, how I think of this is that atoms either want to have an empty shell, so in other words, they want to get rid of that electron, or they want to have a full shell, right? So these are actually pretty reactive because all they have to do is either get rid of one electron or gain one, and they'll fill this first shell, right? So in the terms of hydrogen. If you go to the other side, right, all of these elements here in the last column of the periodic table are full. So they really don't want to react with anything. A full shell, and you may remember this from chemistry, is, 2 electrons in the first shell, 8 electrons in the second shell, and 8 electrons in the third shell, right? So all these are full, but right next to this, as we were speaking about chlorine in the last presentation, see how it only has, if you count them up, 7 electrons in its outer shell, which means it really wants that last electron. Remember, atoms are the happiest when their shells are either full or empty. So it's going to react with things too. So um, elements in the middle, like carbon, though, you can see that it's got 4 electrons in its outer shell, can go a multiple number of ways, which is why so many molecules in living things are based on carbon. So it's all about those valence electrons. The electrons in the very outermost shell are the ones that determine bonding, what bonds can be made between different elements, as well as what charge the element is in a given situation. And that's going to be extremely important to talk about as we go through biology, because this is how we're all made up, of course. That's the reason that I'm telling you all this, is that, our body's structure is made of bound atoms or bound elements in the form of molecules. And a really big part of how our physiology works is based on charged atoms in our bodies, and we'll talk more about that later when we can apply it. So how do atoms come together to form molecules and compounds? Well, there's really two different ways. There's ionic bonds, where literally one atom will steal an electron from another. The charges will change, and they'll almost have sort of like this mutual attraction, right? I don't know if you can see it. I know it's a little bit small, but maybe you can zoom in on your screen. Sodium, when it's in solution, like when it's in water, has a +1 charge, okay? Well, why does it have a +1 charge? Because it got rid of an electron. Where did it go? That electron actually went to chlorine, and chlorine gives it, or that gives chlorine, rather, a negative charge. Okay, so what's going on here is, if you remember back in the periodic table, sodium, actually I'll click on it really quick. Sodium, here we are, has 1 electron in its outer shell, right? Chlorine has 7 electrons in its outer shell, right? Remember what we said, in order to be the happiest, the ground state, an atom either wants to empty its outer shell or fill its outer shell. So in other words, it wants 0 in this case, or 8 in this case, right? Well, if sodium has 1 to give and chlorine needs 1 in order to be happy, then really what happens when you put sodium and chlorine together, sodium donates, whatever you want to call it, its electron to chlorine. Well, what charge is an electron? Electrons are negatively charged, right? So if sodium gets rid of a negatively charged electron, it's like subtracting a negative, right? What does that mean? That means sodium is now positive. Now, chlorine got the electron from sodium, right? So what happened? It received an additional negatively charged particle, an electron. So that means chlorine is now negative. Now, if you think about it, if you put a positive charged atom next to a negative charged one, you guys probably know this. What do you know about opposite charges? They attract each other, right? Just like people, opposites attract. So what that's going to do is literally hold them together, hold sodium and chlorine together by this sort of like this electrostatic charge. It's almost kind of like a magnetic, really, charge. Not physically magnetic, but that's what it acts like. You know, they stick together. Okay. So that's the one type of bond that we can form, which is called an ionic bond. Covalent bonds are where atoms are actually shared instead of donated, right? So in this example here, you have carbon and 2 oxygens. So what molecule is that? Exactly right. It's CO2, right? So that would be carbon dioxide. So what's going on here? Remember, if you remember, we'll go back to this one again. I think it's easier to see. Carbon has 4 electrons in its outer shell, right? Which means it can either lose 4 or it can gain 4. It's equally probable for carbon to lose all its outer electrons as gain 4 more. Oxygen is more electronegative. In other words, it really wants to gain electrons because it's easier to gain 2 in its outer shell than lose all 6, if that makes any sense. Okay, so again, we'll talk about this and we can go over this in detail if you need to brush up on chemistry. So what happens then is 2 of those carbons are donated to each oxygen. Okay, so remember, carbon has 4 to give. Each oxygen wants 2, right? So if you split the difference, carbon can give 2 of its electrons, you can see they're the green ones here, and share them with oxygen, right? Sorry, there's a car going by. Got my windows open. Carbon and does that for both oxygen atoms. Now, what happens though, instead of carbon having all of its electrons stripped off, it'll share them, right? So it'd almost be like this figure 8 pattern where the electrons are holding these things together. That's what we call a covalent bond when electrons are shared, as compared to an ionic bond where electrons are donated, right? So I think this is an important distinction. Covalent bonds are much stronger bonds than are ionic, okay? And most of what you're going to see in the body, all the materials that, make up our bodies and cells and that kind of thing are covalently bonded molecules. Okay, so just to show you this in another way, a covalent bond, so you have these 2 hydrogen atoms, basically what they're doing, these little blue clouds represent the electrons, and where they could be at any particular time in space. So this is these 2 hydrogens sharing electrons. So if you think about it, each one of these electrons has, or sorry, each one of these hydrogen atoms has 1 electron, right? And this one has 1 electron. Well, what do they want to have in their outer shell to be happy? They want to have 2. So if they come together and these electrons are literally going like this and they're sharing 2 of them, essentially it's like for any moment in time, each one of them has 2 electrons because it happens just so fast. These electrons are just zipping around their nuclei super, super fast. And that's what makes hydrogen. It also makes a whole bunch of other bonds too. The same thing would happen with oxygen, like O2. Okay, so what do covalent bonds do? A molecule consists of 2 or more atoms held together by covalent bonds, right? A double covalent bond, or a double bond, is the sharing of 2 pairs of valence electrons. You can also have triple bonds, or rarely quadruple bonds. I don't know if I've ever seen a atom or a molecule in biology ever act like that, but we're just going to compare and contrast the two for a couple more slides. So what you have here, as I was just saying before, 2 hydrogens, right? Normally, if these were separated, each hydrogen would have 1 electron. Now, because they're together, they can literally share those 2 electrons, essentially making them have 2 in each outer shell, right? And what it looks like is, well, you use your own imagination. A peach, we'll say. Okay, so that's what it looks like in the space-filling model over here, okay? A double covalent bond, like in oxygen, is the sharing of 2 pairs. So that would be 4 total, right, electrons between the 2 atoms. So you can see that there's a pair here and a pair here. What this leads to is a double bond between the oxygen atoms. all the outer shell for both atoms essentially has 8 in it, so you can go around this way and count for the right atom and go around this way and count for the left one. They all have 8 electrons in their outer shell, okay? And that makes each atom happy and they stick together, and it's a relatively strong bond, okay? Now, single bonds can be created, of course, between different elements, right? So far, the last two examples we talked about hydrogen basically sticking to itself and oxygen sticking to itself. Well, what if you stick hydrogen to oxygen, right? Well, if you think about it, oxygen here has normally 6 electrons in its outer shell if you go back to the periodic table. Hydrogen has 1 in its outer shell. So what can you do to make these atoms, happy with each other? 2 hydrogens can bond with a single oxygen. Hydrogen has 1 electron to donate, right? So 2 hydrogens would therefore have 2 electrons to donate, and that's all oxygen needs to fill its outer shell, right? And in so doing, these hydrogens can also share electrons with the oxygen. So that means all 3 atoms are happy to do this, right? This happens really often in nature, right? Because what is H2O? It's water. Water's everywhere. It covers 75% of the Earth's surface, right? So that would be a very, very stable compound because everybody's sharing electrons. Now, methane, which is a hydrocarbon, technically, it's got 1 carbon and 4 hydrogens. It's pretty common. You guys probably heard of methane gas being released from the ground or from cows, that kind of thing. So carbon, remember, has 4 electrons in its outer shell if you go back to the periodic table. Each hydrogen has 1, right? So how many hydrogens would carbon want to bond with to fill its shell? It would want to bond to 4 of them, right? So what you're seeing here now is a relatively symmetrical molecule, that has 4 hydrogens bonded to 1 carbon. So everybody shares, and you can see that this hydrogen got 2, right? 2, 2, and 2. The carbon itself has 8 because it's sharing 1 with each of the 4 hydrogen atoms. Okay, so if that wasn't enough chemistry, kind of a crash course, because again, I assume all of you have, had the prerequisite or, taken chemistry at some point, not in high school, in college so far. Electronegativity is an atom's attraction for the electrons in a covalent bond. Okay, so this is kind of a weird thing. So, how we said that, like water, right? It's sharing 2, actually, I'll go back to the picture here. So water is sharing 2 hydrogens with oxygen, right? Well, oxygen being a bigger atom, it's got more pull on those electrons than the little wimpy hydrogens do out to the outside, okay? So what that means is, now if you were to think about this, even though these electrons are being shared by all 3 atoms here, oxygen has a greater pull. So in a sort of like a time if you were to do like a time-lapse camera view of what's going on here, because oxygen has a greater pull, the electrons are going to spend more time around oxygen than they are zipping around hydrogens, because oxygen pulls on them stronger. So what that means is oxygen is essentially, in this element, going to have a more negative charge, okay? We call that a polar covalent bond. When the charges are even between all the players in a molecule and the electrons spend equal amounts of time around each one of the atoms in a molecule, we call that a nonpolar covalent bond. So hopefully that'll make more sense here. Here's your water molecule, right? Big oxygen, smaller hydrogens, right? These little lowercase deltas here, this is a positive partial charge, or a partial positive charge. Here is a partial negative charge. The reason that that happens again is because oxygen pulls more strongly on electrons, forcing electrons to spend more time around the oxygen than they do around the hydrogens. So what does that do? Well, electrons are negatively charged, right? So if you're having these negatively charged particles spend more time around the oxygen, that makes the oxygen side of this molecule, because keep in mind, they're all still stuck together, right? The oxygen side of this molecule is going to be more negative than each of the hydrogens. The hydrogens just don't pull on electrons as strongly, so the electrons are spending more time around here than they are around the hydrogen, okay? This is what we call a polar covalent bond, because one side is one charge, so the oxygen side of water is a negative, and the hydrogen side of water is a positive.